Everyone, welcome to the Taiwan Space Union online seminar series. This series consists of a sequence of talks discussing the possibility of setting up an early warning system of tsunamis. And as we know that such programs have been organized in the USA or Europe already, or some are doing, or some people are doing that, but then not so much in Asia. And the AOGS, the Regional Advisory Committee, started an initiative which is to try to see whether the scientists or experts in Asia could work together. Because this is an interdisciplinary field containing space science, atmospheric physics, oceanography, and then even land-based facilities, and as well as data analysis center. So it's a good way, to organize a cooperation, regional cooperation. And we have already 5 or so such online talks already on this topic given by different experts from UK, from France, from Taiwan, and USA. Today we are very happy to be able to invite Professor Donsub Lim, who's a young assistant professor in the Department of Mathematics and Statistics at Washington University in St. Louis, to talk about a very important step, which is if in case you do have tsunamis, and you do get signals from the ocean-based detector or ionospheric based detector system, and how can you analyze them, in real time, almost in very short time, to say that this is for real, right? And then you better be careful to alert the early warning network, and then so people could prepare for the upcoming events. And Professor Lim himself is a mathematician, and he applied his methods to many things. And surprisingly, he's even applied his method to plasma physics. But that would be some other time we will listen to him. But today we listen to him about the tsunamis. Yeah, Professor Lim, please go ahead.
Okay, let me try and share screen. Okay, thank you for the invitation. So today the talk is going to be about towards accurate and stable tsunami warning, early warning using neural networks. So we tried training neural networks to do real-time tsunami predictions, but as you will see, there is some there are some issues with neural networks that perhaps is not too widely known in many domain fields. So I will talk about that. Then that problem has to be solved before we can actually use neural networks for tsunami early warning in practice. Okay, let me try to go to the next slide. Okay, so the outline is as follows. I'm going to talk about tsunami early warning work that we've recently done using convolutional neural networks. And then I'm going to talk about this issue I just mentioned, which I will mention the need for a kind of a stability analysis for neural networks. And we have our sort of a little bit of a first progress on this topic, but it is a very much an open topic. And then I will talk about our more recent work that uses a real-time tsunami prediction using just geodetic measurements, so earthquake measurements. Okay, so the objective of our research is to try to do real-time tsunami prediction. So in the event of a tsunami-genic earthquake, we'd like to predict maximum inundation levels at important geographical locations sufficiently early so that it will be helpful towards emergency management. Of course, this real-time prediction model can also be potentially be used for probabilistic tsunami hazard assessment. because it will really save computational time to predict tsunami inundation patterns. So this is joint work with Chris Liu, who was a graduate student at University of Washington at the time, Bobby Baraldi, who was at Sandia National Laboratories, and Randy Levesque, also at University of Washington, and Kinji Otera at the Tohoku University. And thanks also to graduate student Shinseng Chin, who's a tsunami simulation data that we've been using, and also to Diego Melga, whose MudPy code we've been using to generate synthetic earthquakes. And there are similar related works which are attempting similar attempts to use neural networks and leverage deep learning models to predict tsunamis. So there is this well-known work, early forecasting of tsunami inundation from tsunami and geodetic observation data, and also machine learning-based tsunami inundation prediction derived from officer observations. So these attempts are quite similar. The difference is maybe the setup of which geographical locations you're looking to predict the tsunamis in, how the earthquake source was generated, and what the neural network model is, and what the data set consists of. There are variations, but these are very similar approaches which appeared about the same time. Okay, our earthquake slip model for generating random earthquakes is the Okada model. So I probably don't need to, you probably know this a lot better than me. I'm a applied mathematician by training, so I only learned this over the shoulder from geoscientists that I know. So our earthquake model is we take, for example, a rectangle or a triangle that represents the fault geometry. And then we slice this up into smaller rectangles, and we assign an amount of slip on this fault. And so you have a random input parameter, which is the slip distribution, the amount of slip on each of these divided up subfaults, rectangular subfaults. Therefore, a vector of slips, the amount of slip that occurs on each of these tiny rectangles, represents one earthquake event. Triangular fault geometry, although I'm showing a rectangular fault here, we've now moved on to using triangular fault geometry. Triangulation is preferred to represent a curved fault geometry. Of course, the precise location of the fault, of course, they're not as rectangular and nicely shaped. So a triangulation is usually preferred. And this is what we use in our experiments. So we take, for example, the Cascadia subduction zone, where we obtained it by meshing the slab 1.0 geometry. I know there are more modern slabs out there, so slab models out there, so this can certainly be updated. So we take the fault, and then we kind of triangulate it using a rather large fault geometry and triangular subfaults. And we assign an amount of slip on each of these subfaults. And of course, this becomes a very long vector, and sampling that vector becomes a problem on its own. So we assume the method we use to generate random earthquakes is to use a Karhunen-Lobe expansion approach, which was proposed in this paper Levesque et al. In 2016. And it essentially tries to do Karhunen-Lobe expansion, which expands the random variables a lot according to some correlation lengths that was recommended to us by seismologists. We do some more nonlinear things on top of the Karhunen-Lobe expansion, which was explained in this paper. We taper, we about the epicenter, we kind of cut off the slip patterns to localize it. But otherwise, we stick to the standard KL expansion of assuming some spatial correlation kernel. Okay, and so of course this slip pattern deforms the seafloor, and that seafloor deformation is given by the Okada model. I mean, this is a triangular Okada model, so we follow the formulas from an older paper, Komnenu and Dunder's paper. And there is a very nice paper by Mead in 2017 that explains all of this really well. And the seafloor deformation is then used as a vertical displacement of the ocean surface, and those provide the initial conditions to the shallow water equations. So we assume an instantaneous uplift. I know there is a lot of physics that goes on in that small period where there is an earthquake uplift and there is a surface elevation on the of the water column on top of it. But we simplify all of that and assume that the lift is instantaneous. So, for example, we generate this random earthquake, and then that causes a surface elevation of the ocean, and then we plug that into our shallow water equations as initial conditions, and then propagate the tsunami forward. Our tsunami propagation model is a depth-integrated model, the shallow water equations, which is a nonlinear hyperbolic system. Here I'm showing a 1D version. So this is a system of hyperbolic equations with a stiff source term. And of course, this h is the surface height, and u is the velocity, v is the bathymetry, g the gravitation constant. And this bathymetry is, of course, it varies very roughly across the ocean bottom, and we assume a constant friction coefficient. And although this is a 1D model, the 2D model can be obtained by rotation invariance, extending this into 2D. So the numerical method that we use to propagate the tsunami is the GeoClaw software, which was developed by Randy Lebec and Marcia Berger and Dave George and Cal Mandley and many others over the years. It's a finite volume method based on solving Riemann problems. It uses a wave propagation algorithm. It uses adaptive mesh refinement. It is well refined. It uses wetting and drying for modeling inundation. There's also an adjoint method for guiding AMR. So all of this software, it took decades to develop and is available as open source software. Underneath, it's just running Fortran code, but it has a Python wrapper and has an OpenMP parallelism. Okay, so we use a GeoClaw to propagate the tsunami. And to give an example of how the AMR operates, here is an example that's available in the ClawPack webpage, a quick simulation of the Chile 2010 earthquake. And as you can see, these are the coarse meshes, which are covering very large regions. However, as you approach the regions where the tsunami is propagating locally, you see that it's refined finer and finer. And in this region where I'm pointing, the grid resolution is very high. So it'd be sort of impossible to put grid edges there. So we've removed the grid edges. And as the tsunami propagates forward, these grid patches that are the refined grid patches follows the wave, and so you have a much more efficient computation of the tsunami propagation. Okay, there are challenges for doing this tsunami, propagating the tsunami and predicting its waveform in real time. To utilize the simulation, the initial condition must be determined, and of course, at the time that the tsunami is occurring, the initial condition is unknown. A source inversion has to be performed. So this requires to recover the initial condition. You need some type of a source inversion. For example, you try to recover the slip distribution from the seismic waves, or you can try to use the tsunami wave height measurements to inform the source. But all of this is in itself a difficult inverse problem, and oftentimes it takes a little bit of time to calculate the initial conditions. Of course, even after your initial condition is known, and your seafloor deformation is computed, which is quite fast to do. Once the initial condition is known, the tsunami simulation can be performed. However, the wall time for a tsunami simulation, even at a very coarse scale, tends to be tens of minutes. And also the simulation results contain a significant level of uncertainty because at the time of the simulation, the initial condition is also uncertain. So these issues make it very difficult to do real-time prediction. A more direct approach is to use regression models, which is the data-driven approach, which I'll talk about. However, I am also working on a reduced order model approach, which can potentially allow real-time simulation rather than turning to a surrogate model, which is based on regression, data-based regression, that is. Okay, so what we'll talk about today is a couple of results that we had from a few years ago, where we set up a regression problem. What we did was from the Cascadia subduction zone earthquakes that we've generated randomly, as I explained before, we tried to measure what the tsunami time series will be, the time series of the surface elevation at these three locations, buoy locations. So 702 at this entrance of the Strait of Juan de Fuca, and this 901, which is in Discovery Bay, and this 911, which is at a point where the Salish Sea connects with the Puget Sound. So what we wanted to do is, since there is this very nice geometry and there is this incoming tsunami wave, it has to enter through this strait. We thought maybe we can take a small measurement at this buoy at 702 and try to predict what tsunami waveform will be at 901 and 911 at later times. And we thought because of this channel, the incoming wave will be mostly a planar wave, and that'll simplify the tsunami propagation. So what we did was, as the tsunami starts coming in at 702, we start our observation window. We took two observation windows, a 30-minute window and 60-minute window. And from that detected wave, we wanted to forecast what the tsunami surface elevation will be for the entire forecast window, which is about, I believe, 6 hours, 5 to 6 hours after the tsunami starts entering the strait. So from 30-minute to 60-minute measurements, we'd like to make predictions as to what happens much more near the Puget Sound over a series of hours. Okay. And let me show how this tsunami simulation is done. So this is one instance of a near-field synthetic Cascadia subduction zone event. And this is 1 minute after the earthquake has occurred, and then 60 minutes and 38 minutes, and so on. And of course, you see that now, after the earthquake has occurred, maybe an hour or so later, the wave starts entering the strait at the top. And then near Discovery Bay, it starts entering after 2 hours and 46 minutes. And then our buoy is placed around over here. Of course, a buoy actually doesn't exist. This is a hypothetical buoy that we played for our numerical experiment. And you see that there's a lot of nonlinear sloshing. So for example, there's positive elevation and then negative elevation. So it sloshes around, and all of this is nonlinear due to the shallow depth near Discovery Bay, where the tsunami shallow model is highly nonlinear, and it does incur inundation, which makes the sloshing pattern hard to predict. Okay, so we randomly generated 1,300 earthquake realizations, and we performed the tsunami simulations for those earthquake realizations. And we filtered out some scenarios that had negligible tsunamis at the strait, which is sort of interesting. I believe it is still a difficult task to know whether there will even be a significant tsunami, even if you know what the slip pattern exactly is. So that reduced our data set to be quite modest, to be 959 realizations, and we did a 8-to-2 training versus test set. And then we trained in an ensemble of 25 neural networks to take as input the partial data of the incoming wave in the observation window. And in particular, our neural network was set up as what's called a DAE, so a denoising autoencoder, which will take the signal from the observation window. Let me go back. So it will take the signal from the observation window and try to reconstruct both the entirety of the time series at 702, the Bowie 702, and 901 and 911 all at once. So the input is, again, to this 30-minute window or 60-minute window just from 702. And then it'll try to reconstruct all three of these signals over the simulation time. And so these are some predictions at the Discover Bay 901. 901 was the hardest Bowie, the tsunami waveform to predict. And since we have 25 neural networks, they all give slightly different predictions. And so you'll see 25 of these curves. And as you can see in the beginning, there's a lot more certainty. And then as the later predictions continue, you'll see that they diverge a lot. And this represents that there's more uncertainty for predicting later part of time series than compared to the first part. Okay, so a prediction, for example, this is the input that was given for the 30-minute window, and then these are the predictions. And since we have an ensemble of 25, what we did was put the orange bar where the orange curve where the mean prediction is, and then we put we fit a normal distribution around the sample of 25 different time series, and we put a band around 2 sigma. We would put a standard distribution, and then these bands represent 2 sigma plus and minus 2 sigma off of the mean prediction mu hat. Okay, and as you can see, if you use 30 minutes of data, it does a decent job of matching the phase and the amplitude, perhaps. But then it does a much better job if you increase the observation to 60 minutes. So if you increase the observation window to 60 minutes, it basically predicts the sloshing around at the Discovery Bay pretty much accurately. There is a visible improvement. And so what we can do is for each of these events in the test set, what we did was we tried to predict the maximum surface elevation over the 6-hour window. And on the x-axis here we have the observed, which is the true maximum surface elevation over all time at location 901. And on the vertical axis we have the predicted. And of course, our prediction it contains uncertainty. So this dot is the prediction, the maximum surface elevation over the 6 hours for 901. And this is the mean prediction. And then the vertical bars represent, again, the 2 sigma plus 2 sigma prediction level. So as you can see, much of the vertical line does overlap with the 45-degree line, which would be the perfect prediction agreement between perfect and predicted and observed predictions. And an important thing to notice here is that the gray dots are the training sets. And there isn't too much of a difference between the prediction accuracy between the training set and the test set. Which is always something to watch out when you use regression models. You want the quality of the training set and the test set to be similar so that you don't incur this generalization error. About that. So we also tried using tsunami-generated tsunami waveforms that we know for sources that weren't exactly generated from our Karhuna-Lowell model. So these L1, B hole, and SA hole, and Wang 1700, these were sources that were generated from completely different means, for example, using the logic tree approach. And so for those models, although they were not in the training set, we could also generate the tsunamis at the gauges for these different sources. And then we could also try to make a prediction. So that's what these blue triangle, the pentagon, and the star, and the hexagon is. And for these, it's still, while they were not in the training set, it appears that it does a decent job of predicting sources, well, the tsunami wave patterns from these sources as well. However, all of this improves a lot more when you have a window of 60 minutes, and you see that the alignment is quite good. Okay. And we did some study comparing it with the more traditional models, such as support vector machines, random forest regression. We also tried using a different autoencoder approach called the variational autoencoders, which has uncertainty built into them. And out of all of those, the VAEs and the DAEs, which are the modern neural network architectures, they seem to do the best job. So over here, the lower and left is better, and you see that for 30 minutes, you get a mean absolute error around 0.3, and then for if you 60 minutes, you get significant level of improvement, mean absolute error around 0.1. Okay, however, that approach of using tsunami measurements, it takes time. As you've seen, we needed maybe 30 to 60 minutes of tsunami measurements to make predictions. However, that's too long of a time if you have a near field event. So we were thinking maybe we can use only geodetic measurements to make predictions of this tsunami wave height. And during the 2011 Tohoku event, after the earthquake occurred at 2:46 p.m., it took about JMA quickly issued about a 3-meter tsunami warning, I believe, and already the tsunami waves started arriving off the coast of Kameishi. There was a 6.8 tsunami reported at 3:12. So I guess you have about 20 minutes before it starts hitting the shore. And so, of course, you can use the GNSS signals, so geodetic measurements of the earthquake, to estimate the source and then run a tsunami simulation. And there was this study quite a while ago. I believe maybe the wall time has improved since then, from 2017. If you use a supercomputer, then it still takes 10 minutes. And total prediction computation maybe takes 20-30 minutes. So the amount of the time that it takes for the tsunami to arrive on shore is roughly about the same time it takes for you to make a prediction. So the early warning system cannot be based on this approach. Well, unless the simulation drastically improves, but these simulation codes have been optimized for a while, and I don't think there will be a big jump in its performance in the near future. Of course, it'd be great if there are these improvements, but so far, recently, there hasn't been a big jump in improving these complicated solvers for partial differential equations. So we wanted to look into real-time prediction using GNSS signals only. Since the neural network is just a regression model, instead of feeding it the surface elevation data, we said, okay, maybe we can generate the seismic waves and put in geodetic measurements instead. So for each of the random earthquake sources that we've generated for our tsunamis, we also ran the MudPy software, which is able to compute the dynamic displacement from earthquake events. This approach is a very simplified approach using Green's functions for assuming a multi-layered half-space model. So it is essentially a one-dimensional model, and really it assumes that the layer of the Earth is homogeneous for each of the layers. And using a Green's function approach, you can computationally compute these fairly quickly. So it does not involve a lengthy time-stepping simulation for more complicated models. So we took this model, and for example, we picked some about 60 stations on the west coast of the United States, and I believe these are in deployment already. So these GNSS stations are already in place, whereas the buoys that we placed for the previous experiment at the Strait of Juan de Fuca, those do not exist yet. So these are already instrumentation that is available. And so we picked some of these stations, and the ones that are starred over here are shown on the right, for example, for one event. And so the measurements we were using, we were going to use both the horizontal, vertical, so east, north, and vertical displacements. So 3 fields over a time of 8 minutes. And of course, the seismic waves travel a lot faster. So when you have 8 minutes of data, you can see that most of the earthquake has already passed through the entirety of the West Coast. So you already have a lot of time series data. Where, as opposed to in the previous experiment, we had to wait 30 to 60 minutes for the tsunami to register at the strait. So we also trained a neural network to do this prediction, but we also wanted to check how far we can go using fewer and fewer stations. So what we did was we tried varying the number of stations from 10 stations, 20 stations, step by 10, up to 60 stations. And then we try to spread them out evenly as much as we can, although they are admittedly concentrated more on the coast. And then we try to group, two different groups of stations. For example, a group of nearshore stations, coastal stations, and then inland stations. For these two groups, if we use the geodetic measurements only at these stations, can we still do a good prediction and compare the neural network predictions that we trained just using these groups of stations? We also tried varying time. But I'll talk about the time window in a bit. And the predictions using the geodetic measurements, turns out, was just as good, if not better, than using the tsunami measurements for 30 to 60 minutes. I believe this prediction, the red band, is the prediction at the 901 gauge. So the same gauge that we placed at the Discovery Bay. This red is the 60-minute prediction from the previous study where we used tsunami surface heights. But of course, this denotes the forecast window. So this red and the band was the result I had shown you previously. And then I'm sorry. That was the blue. The blue dashed line is the old prediction. They were quite on top of each other, so it's hard to tell the difference. This red band and this red is the mean prediction using 60 stations, and this band again denotes the uncertainty, 2 standard deviations plus or minus around the mean prediction, and they're right on top of each other. And using the GNSS stations, you can make this prediction within minutes. So within 8 minutes of the prediction, you already have a lot of the GNSS signal. And we'll see that the quality of the prediction does not deteriorate if you decrease the observation window for the geodetic measurements to 4 minutes. I'll show that soon. There is another one where the prediction of the blue, it starts diverging a little bit, but it agrees very well. And again, this is the forecast window. We tried representing this using what's called a Taylor diagram. So the correlation coefficient approach is 1, so closer to this 1, the better. And as you can see, as we change the number of stations that we used for this prediction, you get a better and better agreement as you use more stations around n equal to 60. And this Liu 21 is the previous prediction using the 60-minute window of the tsunami measurement at the Strait of Juan de Fuca. The same here, as you use about all 60 stations of geodetic measurements, it starts getting better and better results. But even at around n equals to 20, you're roughly at the ballpark of the previous study. So closer to this point is better. So n equal to 60 is certainly doing the best prediction in terms of the root mean square deviation. We also tried decreasing the time window. So that is the plot in the middle. And as you can see, once you have about 4 minutes of data, so 240 seconds of geodetic measurements, you start getting pretty good agreement, pretty good prediction. And this square is the L1 test error, which I think is the most reasonable thing to look at. And of course, you can also look at the prediction of the maximum elevation. So how well your time series is capturing the maximum elevation, how accurate is that? And so that's given by these circles. And as you can see, a certain threshold is reached after 4 minutes. So using 4 minutes of data seems to be sufficient to make an accurate prediction. And using about 20 stations appears sufficient as well. When we split the group stations into 2 groups, let me remind you what that is. So these blue groups versus the red groups. So the blue groups are the coastal or nearshore groups of stations, and the red is inland. And then so it seems that if you put if you're forced to use only coastal inland groups, you do worse than having well-distributed stations, which I think is a reasonable conclusion. And the coastal ones are nearer to these events, so I believe that causes the coastal group of stations to be a better set of sensor placement compared to the inland. So the conclusion is if you do 20 to 30 well-distributed stations and 4 minutes of GNSS signal, I think is enough for the neural network to make accurate predictions. Okay, there are, of course, open problems. There's a how do you predict inundation patterns? That's a 2-dimensional image. We want to look at geographical areas. So this led us to generate a new data set. We actually tried doing inundation prediction for a little while, but we had no luck with the data set size of a few thousand. And then we tried increasing the data set size to 6,000. That also didn't seem to work very well. So we looked at, inspired by the MNIST data used in computer science, which has a data set size of 60,000. We started generating more tsunamis, and now we have a brand new data set of size of 71,000 events off the coast of Japan, so near the Nankai Trough. But it's still ongoing work. We weren't able to really do as good of a prediction for the 2D inundation yet. I think we needed a bigger data set size, and we were currently working on doing inundation predictions. Okay, so those are open problems. But then we quickly realized that the neural networks actually have a bit of a problem. So I'll talk about the stability of analysis of neural networks for a little bit. We would like to analyze the stability. The goal of this study is inspired by the fact that the neural network models they're known to be unstable with respect to certain small perturbations in the input, which is a big problem. And we would like to provide an analysis of this phenomena and characterize the space of perturbations that cause these instabilities. And of course, the eventual goal is to make the neural network predictions more robust with respect to these instabilities. This is joint work with Sana Suri, who has since graduated and who's now at UC Davis as a postdoc. Sang-Hyun Hong, who is a faculty at Oregon State, Kuk-Jin Lee at Arizona State, and also Randy Lebeck, also who is responsible for the GeoQual software. Okay, so I'm not sure if this is widely known in your group or not, but for this audience or not, but there is a need for stability analysis. And sometimes this instability goes by the name of adversarial examples. Because geodetic measurements for these GNSS stations, they always come with noise. We would like the neural network predictions to be robust with respect to input noise. And there's this paper by Shegedi and others where I believe the title is Intriguing Properties of Neural Networks. If you fix input to the neural network X0, and you can find bad perturbations that will yield a very different prediction output for your neural network model. So what they did was they trained a neural network image classifier that would correctly classify these images on the left. For example, a school bus, I believe this is an ostrich, and then this is a pyramid, soap dispenser, mantis, and a dog. So these left images, the neural network was trained to predict correctly. However, if you add a little bit of perturbation, this noisy-like object, you get an image on the right. This added to this image yields the image on the right. And this image on the right looks exactly the same as the left image because the perturbation is very, very small. So this delta X perturbation, which is this middle column, is very, very small. However, if you input these images to the neural network to predict what it is, the same neural network that was correctly classifying the images in the left column will classify all of the images on the right as ostriches. And this is called an adversarial example, and it is found by a type of a gradient descent called the projected gradient descent. And let me, to provide a brief introduction to our mathematical analysis, let me introduce some notations representing feed-forward neural networks. So feed-forward neural network is an alternating composition of an affine mapping and a scalar nonlinearity. And so these affine mappings are defined as a matrix multiplication to the input plus a bias term. And these weight matrices are made up of these entries. These biases are also made up of these entries, which are parameters of the neural network. And the sigma we often take to be the ReLU activation, a nonlinear function that simply takes the maximum between 0 and its input value. So it just sets the negative values of the input to 0. So a neural network, for example, a convolutional neural network or residual neural networks, these common architectures can be written as a feed-forward neural network, which just takes the input, applies an affine mapping, and then applies a nonlinearity, and then it repeats this concatenation about L times. Okay. So what we've done mathematically is to consider something we call a low rank expansion of the neural networks. So if we look at the ReLU function, which again just kills out the negative entries, you can write the application of a ReLU to a vector z as a half of z plus the absolute value of z. So this is the original vector z. And this absolute value of z is, it just takes the absolute value of each of the individual entries. And if you're an applied mathematician, you see that this, it is often, we talk about how this mapping z to the vector of its absolute values is a reflection vector. In that it preserves the length of this vector. It just points in a different direction. And it is, in applied mathematics, it is quite common to write this as what's called a Householder reflection. So this operation of mapping z to absolute value of z, you can write as an identity matrix minus 2 times some vector v sub z times v sub z transpose. So this matrix, it has rank 1. So if you, for example, take the singular value decomposition, it has a 1 non-zero singular value. And so if you write the function of this absolute value z as this h of z, since ReLU was half of z plus absolute value of z, you can write the absolute value of z as a hz times z. And of course, this identity matrix will multiply the z to give the z again. And writing out this term, we get identity minus some vector vz transpose times z. And omitting the bias, each layer in our neural network, we can expand as the identity minus this rank 1 perturbation vector. And if you do some calculations, you realize that you get a weight matrix. The application of ReLU can be written as a multiplication by the original weight matrix and rank 1 matrix M sub L. And it's important to note that this M sub L is a matrix that depends on the Z. So using this expansion, you can write a feed-forward neural network that we've seen before. So therefore, convolutional neural networks or residual neural networks as a matrix multiplication. So f of x is some matrix f, capital F, times x. But this matrix, of course, is input dependent. It has to be, because f of x is a nonlinear function. You cannot expect f to be static. So it has to depend on the input x as well. And this, what's interesting is that this matrix f of x is given in this form where we have the original weight matrix that appear in your Fi mapping, plus a rank 1 perturbation. And then if you expand this, as you would expand a polynomial for example, since there is 2 terms in each of these parentheses, you get 2 to the L terms. So you get a very large number of terms. Where all the possible combinations are you either pick W or M in each of these factored forms. So all of these combinations give you 2 to the L, 2 to the capital L. Then L is the number of layers. 2 to the capital L number of terms. For example, a convolutional neural network might have 10 layers. So you would have about 1,000 terms over here. However, what's interesting is that this f of x can be written as a f0, which is a matrix that multiplies all of the w's, the original weight matrices, and f sigma is the input-dependent part that has at least one m included in this sum. So this f0 is input-independent. It's a linear mapping. F sigma is a sum of rank 1 matrices that are input-independent. And as I mentioned, this is one term out of this sum. This f sigma is a sum of 2 to the power L minus n1 terms. So there's a lot of term there. But due to the structure, this f sigma is actually low rank. And its rank is at most L minus 1, where L is the depth of the layer, the number of layers or the depth of the feed-forward network. And the row and column spaces of this f sigma can be calculated explicitly. So you take this VZL vector, which is the vector appearing in our Hausdorff reflector, and you can multiply out all the later weight matrices. Or you can take this VZL and you can multiply the transpose of all the weight matrices appearing in the previous layer. So this gives you the span of the row and column spaces of f sigma. And of course, this f sigma can be written in SVD form like this. And this is a singular value, the left singular vector and right singular vector. And all of these are going to be input dependent. So every time an input changes, these vectors will change as well. So we call this a low-rank Hausdorff expansion. So to sort of summarize, we have a feed-forward neural network that's written as an input-dependent matrix capital F times the input f, x. And this input-dependent matrix has rank at most L minus 1. And these left and right singular vectors, you can estimate using the calculations for phi and psi I showed in the previous slide. So they're quite straightforward to calculate. And then we can mathematically formulate how these adversarial examples occur. So if this delta x is a small perturbation to the input data, however, that the perturbed vector is somehow causes f sigma times delta x to be very, very large compared to f sigma f0. This is the input independent linear matrix multiplied to delta x. This is, although this might be normally behaved, so it has an order 1 behavior, this might have order of 1 over epsilon behavior. So if one of the singular values in the low-rank Hausdorff expansion behaves like 1 over epsilon, even if your f0 is well behaved. So its 2 norm behaves more or less has the order of 1 scaling. Then F sigma of delta X might have order 1 scaling, although this perturbation is small. So this F sigma matrix might grow this perturbation very big at the order scale of 1 over epsilon. Since X0 approximates F0, the neural network must be also unstable with respect to this perturbation delta X. So that is sort of our hypothesis. So what does this mean for our tsunami model? Let me show this example. So we found just as a neural network classifier was confused by small perturbations, we added a very, very specific small amount of noise at the level of 0.5% to our geodetic measurement data. So I'm showing just a few of the selected signals. Remember, we had 60 stations in 3 different directions, but these are sample perturbations, samples of that time series at 2 stations, BAMF and LSIG. And this was the original input signal. We perturbed it a small amount. So visually, they look about the same. However, our tsunami prediction model, our neural network model, the output changes by 36%. So although the input signal looks more or less identical, the output signal changes by a significant amount. So you can see the maximum prediction changes by maybe 4 to 5 meters, which is a huge amount, although the input signal is essentially the same. So this is a pathological behavior due to the instability in the neural networks. But what we found was that if we projected this perturbation in the direction of the basis direction given by the low rank householder expansion, the perturbation stays pretty much the same, although we have removed some components by projecting it in the direction of the low rank space psi. And then what is interesting is that if we remove the directions of psi, then this adversarial effect appears to disappear. So it seems that our hypothesis is that this basis contains all the bad directions in the input space that can cause this perturbation. So if we can compute this psi somehow, then we can maybe able to project out the adversarial effects. And as you can see, after removal, the original signal and the original prediction and the perturbed output stays pretty much the same. And since the input changes this about is very small, this is a much more reasonable outcome than in the previous adversarial example case. So these are still the problem of coming up with a defensive algorithm or a stabilization strategy is, of course, still an open problem. We were doing some extensive computational experiments with the low rank expansion. And of course, there is a wider machine learning question. Do similar expansions for more recent architectures like transformers, do they exist? Things like this. So these are the references. Here's a stability analysis of neural networks with applications to tsunami early warning. Sorry, this should have been updated. It is now published in Geophysical Research, Journal of Geophysical Research, Machine Learning Computation, the new journal. And the tsunami early warning using GNSS signals, this appeared in GRL in 2022. And the comparison of machine learning paper, this paper used the tsunami surface elevation at the Strait of Juan de Fuca. This is an older work from 2021. And I think that's about all I have. And thank you for your attention.
Yeah, thank you very much for a very detailed lecture. For one thing, I'm amazed that you have done so much work in looking at the earthquake simulations. and as a mathematician, and I think you have done a lot of work. And the later part of the very heavy dosage of mathematics, I think that some of my colleagues might not be able to stand it, but let's see. Anyone have questions here to ask Professor Lim? I have a number of colleagues, young colleagues, if they're still there, if I call them up. See, the problem is that they are working on the ionospheric disturbances. And you're talking about the land-based or ocean-based, the detector system. So
yes, yes, I actually have a question about that. I don't really have a good so everything I learned about geophysics, I learned over the shoulder with my advisor, PhD advisor, Randy Levesque, and Diego Melgar, who's an excellent seismologist. However, I don't really have a deep understanding of the mechanics of mechanics of the Earth and so on. So I was wondering what kind of geodetic measurements you get at the ionosphere. Is it acoustic waves?
They both acoustic wave and gravity wave. Anyone here can give what's the limit an answer? Let me see. 视频你可以在吗？
Yeah, 老师我在，我就想说可以回答。
Why don't you give the answer to
Yeah. So both waves we can observe depending on what kind of the filtering we use, and those perturbations are actually the perturbations of the atmosphere in the ionosphere. But we can observe the ionosphere, the plasma density by the ground-based GPS signal. So we can observe those kind of perturbations, such as in the last page of your presentation, that the second reference you use might be that kind of the method. That so some of us, like this one, the tsunami early warning, this one. So some of us, we see the GNSS perturbation as like a space buoy. So I'm kind of interested in that maybe your method can be used in this kind of issue. Yeah.
I see. I mean, I think as long as you have a way to generate the data set, the deep learning approach just requires a big data set. So I think if you have a way of simulating these ionospheric disturbances, then I think it should be possible. I see. I guess for us, it's really nice. I think that we get a measurement in few minutes, and that I guess these stations are already in place, so you don't really need more instrumentation. However, I think in principle, yes, the same approach can be applied to the the space buoys as you
yes.
you've described them.
Yes, sorry to interrupt, because the ground-based GNSS observation, they can observe oblique observation, so we can see not at the site location, but somewhere far away. So I think the GNSS can also be used very good for the precursor or the early warning of the tsunami, because we can see much more far away.
I see. That's interesting.
Yeah,
it is true that most of these stations are onshore. I guess Japan has really good instrumentation under the ocean near the fault, but they are some distance away. So yeah, we are still looking into whether having the stations very far away still gives you a good accurate prediction or not.
yes.
We're not sure about that. So
yeah, appreciate that. Thank you. Very interesting talk. Thank you.
Thank you for the questions.
And the other audience have questions for Professor Lim. Yan Qilin, 齐彦霖，你在吗？
老师，我在。
Yeah, you have question for Professor Lim.
Just follow the Shiping's the comment, like we use like GNSS data, but for the ionosphere. But the problem that we face is that the ionosphere is very disturbing. Not only like a tsunami, and also has a different things, and originally already have like a TI some kind of traveling ionosphere disturbance, and it's hard for us like to find which signal is from the tsunami. Yeah, like it is for us like we is hard to decide which signal like is from tsunami, because we have a lot of disturbance, and sometimes the original have like only it has like a huge tsunami, like a Tohoku earthquake that is very significant signature, but like a very small tsunami like is hard to define. Like this July, like the tsunami, we found it, but it is hard to define like which signal is a tsunami. So it is a problem like we faced. So maybe like we can use like your method like to like use the the machine learning to define which to help us to find which one is a tsunami signal. Thank you.
Yeah, I guess yeah, that's a much more difficult question, because we also we were using synthetic data, so we weren't really we haven't really tested against a real world measurement where even, of course, these geodetic measurements would also have a lot of noise. So we're assuming that these signals are so significant, and of course, the significant tsunami-genic events must be higher magnitude. So we were thinking that for larger events, the noise will be much smaller than the earthquake signal. If that's also true for the ionospheric measurements, then I imagine you just need to maybe have a denoising algorithm to get rid of noise that occurs usually versus during a tsunami event, I guess. Yeah, I'm not sure how good these methods are for denoising these other disturbances. And I don't really have a feel for how big of a signal you will get from the tsunamis. But if it is really big, then I think these methods might be worth looking into.
Well, this problem has been considered in the earlier talks by a number of people. So I will send you the links, and then so you might want to listen to them, and they'll be very interesting for you. Now I will ask someone from the 海啸研究室哈，那个老师同学们有问题吗 ？Do you have question from the 海啸研究室？
I'm sure your
Hello.
presentation. 有
Can hear you. Yeah. Do you have question? Please go ahead.
Appreciate your presentation. I have some question to ask that. You say that you have to make the data set more larger to simulate the wave height, and I want to ask that, is that you self-generated or it all comes from the buoy observed data?
So I think I understand the question is for, I guess we were talking about the open problem slide. We were talking about how, so for the wave height data, we wanted to predict a 2D inundation patterns. So given a city, we wanted to see what the flooding pattern will be in 2D. So far, all our published work has just been on gauge data, so buoy data for tsunamis. But by inundation, we mean like onshore inundation. So for that, we thought bigger data set. And all of our data is simulated. We don't really have any. We have a few recorded real data, but then there's not really that many.
Okay, thank you.
那个海啸营就是你是中山大学嘛，对不对？
我是中央大学的，
中央大学是吴老师那边的吗？
对，吴老师的。
OK， 是 OK，Thank you。
好，谢谢。
Very good. And anyone have questions for Professor Lim? If not, and I will end this session because it's very, very informative, very interesting. And thank you very much, Professor Lim. You have done a great job, and you're still so young. I mean, I expect so much out of you in the coming days, the coming years. And look, we will contact you again, right? I mean, I think that we are, as I said, that we are trying to start to organize something together, and your work,
of course,
and, everybody's would be very important. And so, thank you again. Yeah, thank you.
Yeah.
And have a good night sleep. Have a good night's sleep. Don't work too hard. Go to bed. Go to bed.
Yes, and if anybody in your group wants to reach out to me, please feel free to email me. I'll be open to discussion.
Yeah, I think they will. Yeah, thank you again. Good night.
Bye. Good night.